Welcome back to day 2. Today we're back to MHD, building off Matt Kunz's introductory lecture yesterday. Today I want to focus on numerical methods for astrophysical MHD. And I will give a little bit of an introduction to build on what he discussed, just to motivate some of the numerical methods. Obviously this is a huge topic. One could give an entire semester course on this, and I'm trying to pack it into one lecture. And so I'm going to have to make a lot of shortcuts. I'm going to make this fairly introductory. If you've been doing numerical MHD, if you've had a course in fluid dynamics, if you've had a course in numerical analysis, then I'm afraid this is going to be very redundant. It's going to cover a lot of material you've already heard of before. But I'm trying to aim this to introductory students who may not have had a course in fluids and may not have had a course in numerical analysis, just to motivate the methods. And moreover, there are many different classes of numerical methods for solving the MHD equations, and I can't possibly cover them all. I'm going to focus very much on one kind of numerical method that's proven to be very, very robust, very, very popular, called finite volume methods, and those we'll talk about mostly today. So, well, by the way, you should have gotten an email with a link where you can download a PDF of this lecture. In addition, there is a homework, as Peter mentioned. I don't really view it as a homework. I view it as a suggested additional reading or work session. I think this afternoon I'm not going to run a particular homework session, but I will be available in this room for anybody who has questions, and I leave it to you to work through the problem set as you see fit. If you're not interested and you don't want to do the problem, totally fine by me. If you want to try some of the problems, great. Of course, I think the only way to really learn numerical methods is to do it for yourself, to either write the code or to use the code yourself. You can't just sit in a lecture and listen to somebody drone on and think that you've learned the methods. You really can't until you try it yourself. So if you really want to go forward in numerics, I think it's important that you try doing some problems, not only just mine, but the others that may be put forward in the other sessions. So yeah, that blue link, of course, is the link that you can also download. So I'm giving 2 lectures. Today is this astrophysical MHD. Next week, I believe on Wednesday, I'll be discussing numerical methods for doing radiation transfer built into an MHD code. So radiation magnetohydrodynamics, flows where radiation field is very important and must be integrated along with the MHD equation. So today, though, we're focusing on astrophysical MHD. As I mentioned, I'm going to start with an overview, building on what Matt said. I'll then introduce some very basic numerical analysis and introduction to numerical methods, and then I'll spend most of my time talking about finite volume methods. I'm happy to answer questions at any time if I go too fast. I mean, the trouble with using slides is I tend to talk quickly and go fast. If you want to stop me, slow me down, ask me questions, that's totally fine. I'm also happy to answer more questions if things that are not in this lecture at any time. So why are we all here? Why are you interested in doing astrophysical MHD? Well, because I think many of the most interesting and pressing problems in astrophysics require us to model the structure and dynamics of plasmas. Because most of the big questions, how do galaxies form? That's a problem in plasma dynamics. How do baryons collect in the gravitational potential of dark matter and turn into stars? How do stars form, either in the Milky Way or in the early universe? That's a plasma problem. How does the plasma undergo gravitational instability, collapse to make stars? How do planets form? Once a star is formed and is surrounded by a nascent protoplanetary disk, how does that disk fragment into the planets that exoplanetary systems we see today? Those are all big questions, and they all require modeling the baryons, modeling the plasma. And so for a collisional plasma, this requires solving MHD equations. We're going to hear about diffuse plasmas, kinetic plasmas, which are treated using very different methods and whose physics is quite different. So today I'm focusing only on the continuum limit, those plasmas where collisions are frequent enough to keep the distribution function Maxwellian so that they can be treated using a continuum approximation using the equations of MHD. And a motivating image, here's a beautiful image of the Carina Nebula, where there's star formation and feedback occurring. You know, this is closely related to all of those problems, big questions we just talked about. You know, this is an environment where there's such tremendous amount of feedback from radiation and supernova eventually in this nebula that it's going to affect the ISM very strongly. It's also a region where stars are forming and perhaps planets around some of those stars. And so trying to understand regions like this requires plasma dynamics. So, and as Matt introduced, to do that we need to solve the equations of compressible inviscid MHD. Now, I agree completely with Matt that CGS are the right units to use, and that's why I'm not using them. In fact, I don't like carrying all those around those factors of 4 pi, and so I tend to just use the magnetic permeability mu as 1 because it sort of scales out of the equations that way. I would just warn you that I'm going to be inconsistent and sometimes have 4 pi's and sometimes not, and I apologize for the confusion that may cause. In these equations, I've set the magnetic permeability to 1. Perfectly allowed to do that, choose units that mu is 1, and here are the MHD equations as written down by Matt. The continuity equation at the top, which is just conservation of mass, momentum equation, conservation of momentum, energy, total energy equation, and finally one of Maxwell's equations, Faraday's law, which gives you the evolution of the magnetic field, where, as he pointed out, the electric field in the plasma is just the inductive term V cross B in the ideal MHD limit, where the conductivity is so high that the sigma is essentially infinite. The conductivity is infinite, so E is minus V cross B. So here, capital E is the total energy, sum of kinetic, internal energy, small e, and magnetic energy, B squared. And P star is just the sum of the gas and magnetic pressure. Now, to solve these equations, these are not yet closed. We need an additional equation, an equation of state that relates the gas pressure to the density and temperature. And it's because the plasma is collisional that we can do this. Because we know the plasma has a Maxwellian distribution function, we know what this equation of state is. Usually we assume an ideal gas law, where for monotonic gas, gamma is 5/3. Of course, we can choose it to be 7/5 for a diatomic gas in the interstellar medium. If you're modeling H2, you can choose whatever you like. In some circumstances, it's useful to use an isothermal equation of state. That is, the pressure is just an isothermal sound speed squared times the density. That's in the approximation that radiative cooling times are much, much smaller than any dynamical time, and so the temperature of the plasma is held constant. In fact, there's another additional assumption, that is that heating times are also much smaller than dynamical times, because if the plasma undergoes an adiabatic expansion, it cools down, it might drop below the isothermal temperature, and so you're assuming there's some mechanism of heating the plasma back up. There's some radiative heating rate, which is also extremely short. So it's kind of a funny approximation, but extremely useful. It assumes that there's both heating and cooling in the plasma that keeps the temperature locked at a fixed value. And in some circumstances, for example, studying supernova, neutron stars, you need more complex equations of state, tabular equation of states. Again, that's not a problem. Insert them into these equations. So to build a little bit more on what Matt was discussing, these equations are known as hyperbolic, or are hyperbolic conservation laws. This is a very important property of these equations. So let's just think about the hydro equations for a second. And note that it's apparent that the equations can be written as a time rate of change of a conserved quantity plus a divergence of a flux is 0. So time rate of change of mass density plus divergence of mass through the boundaries of any surface is 0. Same with momentum and total energy. And so these equations can be written in a very compact form. So it's useful to write a vector u, which is just a vector whose components are each of the conserved quantities. So mass density, each component of momentum and total energy, and where F is just the fluxes of those quantities, so written out here in full form. And so then this equation can be just recast as du dt plus df du dx is 0 from the chain rule. And of course, any PDE, which is first order in time and first order in space, is a hyperbolic PDE. If df du is a constant, this is a linear hyperbolic equation. If df du depends on the solution u, this is a nonlinear equation. Of course, the full system of equations are nonlinear because this is the characteristic wave speeds which depend on the solution u. So they're nonlinear, but it's useful to sometimes look at the linear equations to get started. Now, this is very, very important because the mathematical properties of these equations completely determine the kind of numerical methods you're going to use to solve them. So the methods you use to solve elliptic equations are completely different than the ways you try to solve hyperbolic equations. So it's important to remember these are hyperbolic systems. not only is it important for the mathematics, but it's important for the physics, because hyperbolic equations admit solutions of certain character. Again, as Matt pointed out yesterday, they emit wave-like solutions. So you can write down a solution to the equations as just a constant uniform value plus some amplitude times e to the ik dot x minus I omega t, which is a wave-like solution, where if A1 is small, these are linear waves, small amplitude perturbations. And as Matt asked you, I'm sure last night you all went into home to your dorm rooms, and you linearized the MHD equations, and you studied the dispersion relation for MHD waves. I'm confident of that. And so you've understood the emergence of linear waves from these equations. We're going to talk about both linear waves and nonlinear waves when this amplitude is very, very large. When these solutions are not steady, they're going to steepen into other things. And so here's a movie of a sound wave, computed using a numerical method demonstrating the solution. And I realize that I'm sure that I'm violating Tamara's rules about using the right color table there. That's a really crappy color table. But it makes it look like things are moving, so that's good. You can't tell that that's really a sine wave, but that's what that is. For MHD waves, well, what do is you just take this form of the equation, of the solution, you substitute it back into the MHD equations. You get a linear system, which has a solution only when the determinant is 0, so you set as a condition, and from that you derive this dispersion relation for MHD waves, which is actually a fair bit of algebra, but well worth doing. And what do you see? You see that there are at least 3 wave families. Each family has 2 wave modes. This is it's a polynomial, it's a quadratic in each of these modes. So there's a wave going to the left and to the right, 1 wave each in each family. There's a wave whose frequency is just k dot VA. These are so-called Alfvén waves that Matt mentioned last time. There's also 2 wave families given by this term in brackets. They're much more complex. They're the slow and fast magnetosonic waves propagating at these velocities, which you can derive closed forms for. Now, what's interesting is that this dispersion relation depends on the angle between the wave vector and the Alfvén velocity. And the Alfvén velocity really is the magnetic field direction. This depends on the direction of propagation of the wave and the direction of the magnetic field. So waves in MHD are not isotropic. They vary their character depending on which direction they're going. And this is best understood by using something called Friedrichs diagrams, which are polar plots which show you the phase velocity for each of the different wave families in MHD. What are shown here are 4 different diagrams for 4 different ratios of the sound speed to the Alfvén speed. So that's measuring the strength of the magnetic field. So in this case, when CS squared or CA squared is small, this is a strong magnetic field. Slightly weaker magnetic field, equipartition magnetic field, where the sound speed and the Alfvén speed are the same, and then finally a weak magnetic field, where the sound speed is larger than the Alfvén speed. And the outer solid line is, in each case, the fast magnetosonic wave. So this shows you the speed of propagation relative to the other wave families of the fast magnetosonic wave. And it shows it to you in directions which are parallel to the magnetic field, that's the vertical axis, and perpendicular to the magnetic field, that's the horizontal axis. So first of all, you can see that these wave speeds are anisotropic. They vary with direction. That's one thing. Another thing is that these wave speeds are sometimes degenerate. That is to say, they lie on top of each other. So for example, along the parallel to the magnetic field, for a strong magnetic field, the Alfvén wave and the fast wave are degenerate. There's only 2 wave families parallel to the magnetic field, whereas at any other angle, there's 3. Except perpendicular, then there's only 1. There's only the fast wave, and the Alfvén and the slow go away. So this is what makes MHD particularly complicated and particularly rich in physics, is that it has this very complex structure to its wave families. There are multiple wave families, their physics are different, and they're anisotropic, and so much of the complexity and richness of MHD comes from the simple properties of MHD. Linear wave theory tells you a lot about the nature of MHD. So this is linear wave theory, which Matt discussed a little bit, but we should also move on to nonlinear equations, because after all, the whole point of numerical methods is to be able to solve the full nonlinear system of equations, to not have to make approximations, to not have to assume that solutions are small amplitude. Because in reality, looking at that Carina nebula, it's pretty obvious the fluctuations in density and velocity and everything else are not small amplitude there. So these are truly nonlinear flows, and we need to follow the full nonlinear properties of the equations. And so one of the most important properties of nonlinear solutions to the MHD equations are so-called shocks and discontinuities. So I point out here that hyperbolic PDEs admit discontinuous solutions, and I say remarkably, because after all, in a discontinuity, the first derivatives diverge, and you're solving a differential equation. So it seems remarkable that you can allow these infinities in the equations, but it turns out the infinity in time, the time derivative, is exactly balanced by the infinity in space, the space derivative, and so it all sort of works out. And so the MHD equations admit steady, discontinuous solutions. The simplest example is a so-called contact discontinuity. That's simply a discontinuous change in the density with the pressure and velocity held fixed. So the fluid has a discontinuous change in density that changes its properties, and this is just moving along at constant pressure and velocity. This is a contact discontinuity. But in addition, you can have jumps in the velocity and pressure, and those are called shock waves. They are exact nonlinear solutions to the equations. Both compressive shocks, where div v is 0, flow is converging in the shock, and decompressing shocks are allowed, but the latter actually can be thrown away by physics because they violate entropy conditions. A decompression shock requires entropy to decrease, which is not allowed by the third law, and so these solutions don't exist in nature, even though they're allowed mathematically. And the way that you describe these shock solutions is by looking at the so-called jump conditions. Shocks occur when linear waves steepen into discontinuous solutions. So a plane wave solution propagating in a inviscid flow will eventually always steepen into a shock. It may take a very long distance of propagation, but eventually it always will. So why don't we get shocks from linear disturbances on Earth? Why isn't my voice shocking the people in the back? Because, of course, there's geometric dilution of my voice. The sound waves are being spread out over a sphere, and they're not plane waves anymore. Moreover, the gas in the room has got a little bit of viscosity, enough to prevent this from happening. But in the ideal case, shocks will always occur from linear wave steeping. They will also occur if you have a disturbance, like an airplane. I don't recommend you do this at home. Flying an airplane close to water at supersonic speeds is not something you should be doing at home, but it certainly makes shock waves that you can actually then interestingly sort of see, because of their reflection off the water causes disturbances that you can then, shock waves are normally invisible in free air, but here you can actually see the disturbance created by this airplane. And of course you can see them in nature because a supernova explosion, in astrophysics there are many situations where disturbances are created that are propagating faster than the sound speed in the plasma, and that'll generate a shock wave. A good example is a supernova, and this blue remnant around the edge is the outer blast wave of this supernova, Tycho supernova remnant. In fact, this is not actually a good example of an MHD shock wave, as Anatoly might tell you later in the week, because in fact, the ISM is so diffuse in this region, this is actually nearly collisionless shock. And modeling this blue rim requires incorporating particle acceleration and collisionless shocks. But nonetheless, it's an example of a shock wave in a plasma. So how do we compute the structure of these shock waves? You stand in the frame of reference of the shock. So you imagine there's a shock wave in the flow. You stand in a frame of reference in which the shock is steady. In that case, the flow is moving towards you in the upstream region. It's moving towards you at the shock speed. It's moving at the speed you're propagating. The shock is moving, that's the shock speed, and so the upstream flow is coming towards you at VU. The downstream flow is moving away from you at some unknown velocity, but you can compute what that is because you know that mass, momentum, and energy all must be conserved in this frame. Whatever the mass flux is coming into you from the upstream from must be flowing away from you in the downstream flame. Similarly, whatever momentum is coming into you, whatever energy is coming in must be flowing away. So you can write down in steady state these system of nonlinear equations which relate the conditions in the upstream flow to the downstream flow. And while there's more unknowns than equations, so you can't solve them for each individual quantity, you can solve them for the ratios of the quantity. So for example, the most well-known is the Rankine-Huguenot jump conditions for the density ratio in a hydrodynamical shock has this form here, where this script m is the shock Mach number, the ratio of this upstream flow velocity to the sound speed. And as you probably know or have heard, for the high Mach number limit, then this reduces just to gamma plus 1 over gamma minus 1. And then for a gamma 5/3 gas, this reduces to a jump condition of 4. So no matter how strong a shock you have, in an ideal monatomic gas, the largest jump you can get in the shock is a density ratio of 4. Of course, this changes with gamma, and it changes with the Mach number. And you can similarly derive other ratios for the other quantities. The other jump conditions are more complicated, so I don't do it. Again, I leave this to the reader to sort of solve these equations for each of the ratios of the jump conditions. In MHD, as we saw, the linear waves are much more complicated. The shocks are much more complicated as well, because there's additional equations and additional jump conditions that can be satisfied, and these additional degrees of freedom give you many more kinds of shocks. In hydrodynamics, you just get one kind. You just have a sonic shock. There's one shock. Only the sound wave can support a shock, and so you only have one kind of shock. In MHD, you have both fast and slow modes. They can both support shock solutions. In addition, you can get discontinuities in the alphane mode, and those are called rotational discontinuities. Not really shocks in the sense that the pressure and density changes, but they are a discontinuous change in the solution across the front. So you can discontinuously twist the magnetic field and generate a kink in the magnetic field, which propagates at the alphane speed. This is an alphane discontinuity, for which you can derive jump conditions for the transverse and longitudinal field components. In addition, you can get slow shocks when the perturbing velocity is between the slow speed and the fast speed. You can get a fast shock when the perturbing velocity is faster than the fast speed. You can get so-called switch-on shocks, in which the upstream magnetic field, the transverse component of the upstream magnetic field is 0, and then it's non-zero downstream. So in some sense, the transverse component of the magnetic field is switched on. It goes from 0 to some non-zero value. And similarly, you can get switch-off shocks, where the upstream transverse component is non-zero, but then is 0 downstream. These are very special cases. You know, these are sort of singular solutions in the sense that the parameter space that results in these shocks is very, very small, but they're very interesting for code tests, for example, to see if you can capture these kind of shocks correctly. And so there's a whole zoo of MHD shocks, which are important for understanding the physics. And then finally, to continue with the importance of nonlinear solutions, it's important to talk about instabilities, because after waves and shocks, sort of the next most important class of solutions to the MHD equations are instabilities. Those are modes in which you can think of them as linear waves in which the frequency is complex. And the imaginary part of the frequency either leads to growth or damping depending on the sign. So if the sign is in the form I used before, the sign is negative, then the wave amplitude decays exponentially, and if it's positive, it grows exponentially. And there are a variety of situations where wave modes have imaginary frequencies that are associated with exponential growth. For example, gravitational instability. If you add self-gravity to the flow, compute the dispersion relation for linear waves, under certain conditions they grow exponentially. Thermal instability. Rayleigh-Taylor instability. That's when you have a light fluid supporting a heavy fluid against an acceleration. It could be gravity or any other kind of acceleration. Then that's unstable to fingering to buoyancy modes. The Rickmeyer-Meshkov instability, that's when a shock wave impulsively accelerates an interface and generates an algebraic instability at the interface. Kelvin-Helmholtz instability, when two fluids are in relative motion to each other, depending on the profile of the shear velocity between the two fluids, there can be an exponential instability. And then finally, the magnetorotational instability, which you're going to hear a lot about later on in the course because it's incredibly important in accretion disks. It's the mechanism that leads to angular momentum transport in accretion disks, another exponential instability in MHD flows. So why talk about them? Because often numerical methods in astrophysics really are about trying to understand the nonlinear evolution of these instabilities. So you could label this star formation. You could label this galaxy formation too. You could label this star-planet formation. I mean, all of these instabilities play a role in the dynamics of all the problems that we'd like to understand. And so you, need to understand what these instabilities are and how they operate, and also make sure that your numerical methods are able to capture these instabilities correctly here, I say. So these instabilities are important to understand using numerical methods, and it's important to test your methods using these instabilities. So what do I mean by correctly? And here, it's important to realize what you can do, what is feasible and what is not feasible with what I'm going to sort of specialize to grid-based methods. What does correctly mean? So the dispersion relation for most MHD instabilities usually contain a very broad range of wave numbers which are growing exponentially. There may be one specific wave number which has the fastest growth rate and ultimately will dominate the flow, but in general, the flow is unstable to a very broad range of wave numbers, which corresponds, of course, to wavelengths. But if you're using a grid code and you're differencing the equations on a finite mesh, you can only resolve wavelengths between some number n times delta x, where n is an algorithm-dependent thing, and the total size of the computational domain you're using, L. And n has to be at least larger than 2. You can't represent, for example, a sine wave on anything less than 2. In fact, 2 is pushing it. 4 is probably what we really should be discussing here. So when we say a numerical method gets an instability right, it means that the linear growth rates of all the modes between the smallest wavelength you can resolve in the mesh and the largest are captured accurately. And you want to make n as small as possible. But of course, at the smallest wavelengths, truncation error, and I'll define what that means, will affect the solution. And that truncation error in grid codes is not Galilean invariant. Even though the solution to Eulerian grid codes is Galilean invariant, the truncation error associated with the solution is not Galilean invariant. So if you're studying instabilities where the fastest growing modes are right at the resolution of the mesh, near n, then they're going to be dominated by truncation error, which is not Galilean invariant. So what the picture you get is going to look different depending on what frame you're in. But of course, that's not a bad thing, actually, because you're studying solutions that are dominated by truncation error. They're not the right solutions anyways. You don't need to use different frames. If you just use different resolutions, you would get a different answer. You don't need to boost to a different frame. You just double the resolution. You would resolve those modes better. They'd behave differently. And so if you're studying unresolved modes, then there is an issue with getting these modes correctly. But then that's a warning. You shouldn't be putting much stock in modes that are being dominated by truncation error anyways. So that's what I mean by correctly. An ideal code would have a perfect dispersion relation over the entire possible range of representable wavelengths. So there's no such thing as a perfect code. It always has approximation and truncation error. And it's important to understand the properties of that truncation error and what it means for your solution. So just to summarize, these are all fundamental aspects of fluid dynamics. If you've had a course in fluid dynamics, you know all this stuff already. If you haven't, then hopefully this is sinking in. They make excellent code tests. And often, these instabilities lead to turbulence, and the study of turbulence, nonlinear turbulence, is really what most of us are using our codes for. So they make an excellent application. At some level, most of us are really just studying nonlinear regime of MHD instabilities. So let's turn to, that's sort of an overview of what I think is important to know about MHD in order to understand numerics. And now let's turn to what you need to know about numerical analysis to understand numerics. And then finally, we'll get to what methods we're using in astrophysics, these finite volume methods, at least one class of methods. So again, if you haven't taken a course in numerical analysis, let me just remind you of some very, very basic things. For example, the presence of round-off error in your solution. Again, since this is the first time we've talked about numerics, I think it's worth for me just to put it once and for all, these basic points. The point being that not all numbers on the real axis can be represented with finite precision in arithmetic. And so if you're doing some operation that results in a number that can't be represented, you've got to round to the nearest representable number. And that means if you do that correctly, if you round the number so that there is no machine number lying between the solution, the actual analytic solution and its rounded value x prime, then we say rounding is correct. And the difference between x and x primed is the round-off error. So you do an operation, it results in an unrepresentable number. The computer should represent that by the closest machine number possible with no other machine numbers in between. Now, back in the bad old days, processors didn't used to do that. Not all processors did correct rounding, which was very, very bad for numerical analysis. I think nowadays that is true. In fact, there's a little program you can download called Paranoia. You can run it on any processor you like. It will test whether or not your processor does rounding correctly. And as far as I'm aware, all of the latest generation Intel and so on processors do rounding correctly. You may want to do this for GPUs as well. They're a different family, and it's important that this is done. But the important point here is that it can be rigorously proved that the relative error of a rounded value is always bounded. It's bounded by a small machine-dependent number called the machine precision. That is to say, the difference between the true solution and the rounded solution normalized by this solution is always less than epsilon. And if this fact were not true, computers would not be useful for doing rigorous mathematics. But because it is possible to prove rigorously that the errors are bounded from round-off, then it is possible to prove theorems and do rigorous numerical analysis and know that, and put rigorous bounds on the total amount of error in the solution after any number of operations. So this is a very important fact that underlies the utility of computers in doing computational science. So that's one source of error. The other I've already mentioned is called truncation error. And that is completely different. I mean, we are using numerical algorithms which approximate the true analytic solution. And we're, on a computer, you can only do algebraic operations. And so we're approximating the solutions of differential equations using algebraic operations. And the difference between the true and our approximated numerical solution is called the truncation error. It's got absolutely nothing to do with round-off error. If you had an infinite precision machine, your numerical algorithm would still have truncation error. So truncation error and round-off error are two completely different things. Truncation error is under your control. It's your job to try to make it as small as possible. Round-off error is not really under your control. Because it depends on the order of execution, it depends on of operations on the processor, it depends on the processor itself, how many bits it uses to represent floating point operations. You really have no control. Unless you write machine code, the compiler will reorder operations from what you actually specify in your source code. So the only way you can control round-off error is if you write machine code, which I don't recommend anybody does. So it's really only truncation error which you're under your control, and you're trying to minimize that. Your job as a numerical computational astrophysicist is to try to find methods that reduce the truncation error as much as possible. And then finally, there's three more important concepts in numerical analysis that you should know about: convergence, consistency, and stability. Two of the three most people know about sort of automatically. The first is convergence. That is to say, the truncation error in your numerical approximation should get smaller as your resolution increases. As either delta x or delta t gets smaller, the truncation error should also get smaller. You want to converge an algorithm. It should converge as fast as possible. So higher order schemes are better. So a first order scheme is the sort of lowest acceptable method. And in fact, you should be happy if your solution converges. First order schemes are often acceptable because there are convergence. But obviously, higher order is better. Nowadays, most people are using, in fluid dynamics, are using second order schemes, second order in time, maybe third order in space, second order in time. But I think there's a real opportunity here for high order methods. As I say here, cost and code complexity put a useful limit on how high in order you can go. Going to a 20th order scheme could be quite expensive and difficult to support in the code. And moreover, it's also extremely important to remember that all methods are first order for discontinuities. You can't do better than first order for shocks and contact discontinuities. And if your flow is dominated by shocks and contacts, then it's the error in the shocks that matter, not the error in the smooth parts of the flow. And so it's very important to get good shock capturing in astrophysics. That's a very important property of the method that should not be sacrificed in order to go to higher order. Higher order schemes that have very poor shock capturing properties may not be advantageous in astrophysics, even though they may be for smooth flow. But I think here's a real opportunity. On modern processors, flops are essentially free. The processors are so fast, they're usually memory bandwidth limited. You can do lots and lots of operations sort of for free if you have data into memory. And so going to very high order schemes, which may involve a lot of operations, may be very, very advantageous. And so I think there's going to be a lot of work in the near future in going to high order schemes, and we'll hear a little bit about that. A very different approach called discontinuous Galerkin methods, which have exponential convergence. They are sort of quintessential high-order schemes. They have lots of advantages, and so we'll hear more about them. In addition, in the finite volume community, there are so-called compact stencil high-order finite volume methods that can go to 4th and 8th order. They're also potentially very, very attractive methods in the future. Even though what I'm going to talk about today is mostly 2nd order in time, 3rd order in space, you should be aware that this is an opportunity for the future. So that's convergence. Consistency is another important concept which is sometimes forgotten, I think. Consistency means that the solution to your discrete equations should be consistent with the solution to the underlying PDEs. That is, the solution to your numerical difference equations should not only converge, that is, the error gets smaller, but it should converge to the right answer. Now, this is a subtle point, but important. There are a variety of numerical methods which approximate the actual evolution equations such that they are no longer consistent with the underlying PDEs. And a numerical method built on those will not converge to the correct solution of the PDEs in all circumstances. And so this can be a concern. So just coming up with a numerical method that converges is not good enough. You also must be certain that it's converging to the right solution. And then finally, stability is an important concern. That is, the round-off error must remain small and bounded. I said before that optimal rounding guarantees that, but you can still generate a numerical method which contains unstable eigenmodes, which can be they can be excited or they can be initialized by round-off error. And the solution can be unstable. That is, solutions can be numerically unstable. The numerical solution can grow exponentially, seeded by round-off error because of a poor formulation of the difference equations. And so keeping the errors bounded is also important over all time. So we want methods that are convergent, consistent, and stable, and that's the goal of numerical analysis. So very briefly, let me just describe a couple of methods just to get you started. That sort of build on this numerical analysis. So let's go back to hyperbolic partial differential equations. 1st order time, 1st order in space. Let's make them linear. Let's make the characteristic speed a constant. This is the linear advection equation. It just represents the advection or transport of some profile u at some speed a. So if I have a sine wave in u, it'll just move to the right or to the left, depending on the sign of a. It'll just move at the speed a to the right or to the left. So an obvious approximation to this linear, 1st order hyperbolic differential equation is just a finite difference. That is to say, break up space and time into discrete points, difference the time derivative using the advanced time minus the old time, and difference the spatial operator using neighboring points. Let me try to do this here. N plus 1, n, so time is the vertical axis, x is the horizontal axis. I have discrete points in space and time. I have point j, j minus 1, j plus 1. I'm trying to find the solution in the space-time, and I'm approximating the differential equation by linking these 2 points in time for the time derivative and these 2 points in space using the spatial derivative. Seems perfectly reasonable. It's the first thing you would guess to do. It's the center difference approximations for this equation. However, turns out if you do a little analysis, it really is not very useful because we can do a von Neumann stability analysis. We heard again, von Neumann has a huge footprint here, having developed the first computers here and done the first numerical analysis back in the 1950s on that computer to figure out why his codes didn't work when he tried using simple differencing like this. So what did he do? He realized that, well, this is just a system of algebraic equations. There's an analytic solution to those algebraic equations. And I can just insert what that solution is. The solution to the difference equation has some complex amplitude c to the nth power times the eigenmodes of the solution e to the ikj delta x. I simply insert that solution into this analytic difference equations, and I calculate what this amplitude is, c of k. And I notice that if c is bigger than 1, I'm taking it to the nth power. Every time step multiplies c by itself one more time. So if the amplitude of c is bigger than 1, this is going to run away. Eventually, it's going to blow up because the amplitude is going to be a number 1 multiplied by itself n times. It's going to get run away, larger and larger. And so a requirement is that the amplitude of c be less than 1. But you can see for this finite difference equation, the amplitude of c is never less than 1 unless delta t is 0. This is a great method if you don't want to integrate the equations forward in time. If you just say delta t is 0 and keep the solution forever, that works great. But as soon as you try to evolve it in time, this will blow up. This method is unconditionally unstable. And it takes work to find methods that are always unstable no matter what you do. So you should be very proud of ourselves of finding a method that will never work no matter what you do. But it's easy to fix. And this was realized back in the 50s that if I simply change the time derivative in this forward time centered space numerical approximation, if I, instead of using the old time at j, if I use the average of the time at j plus 1 and j minus 1, and looking at this so-called difference molecule, this pictorial representation of what's going on, you can see there's kind of a problem because the values used to compute the time derivative are completely different than the values used to compute the space derivative. That's fundamentally why this runs away, because there's no coupling between the points used to calculate the time and space derivatives. But if I just replace this point with the average of these two, now the points are all coupled together, and this turns out it works. If I just then do exactly the same analysis, insert the analytic form for the solutions to the difference equation, I get this new relationship for the complex amplitude, and this has an amplitude less than 1 if this condition is satisfied. If the speed of propagation times the time step over delta x is smaller than 1, this is stable. And this is the so-called CFL, Courant-Levy-Friedrichs stability criterion for integrating these equations. If I choose my time step correctly, such that it satisfies this condition, the solution will remain stable and integrate this equation forward in time stably. So that seems remarkable. All I did is change that one term to an average, and it changed completely the result. Why? Why? Because if you're a little more analysis, it's easy to see why. You can force the equation to look like forward time center space. Just rearrange the top equation such that the first term, the time derivative and the space derivative are FCTS, and then the remainder, what's left over from forcing the equation in that form, looks like this. And what does that look like? Well, if you've done any differencing before, you recognize that this is the centered second order approximation for the second derivative, d2u dx squared. This is the diffusion term, where I'd have to pull out a delta x squared on top, and so the diffusion coefficient here is this kappa delta x squared over 2 delta t. So in other words, this form of the Lax-Friedrich equation is not actually solving the linear advection equation. It's actually solving this PDE, a totally different equation, which consists of the linear advection equation plus this term on the right-hand side, which has it's a diffusion term. This is a mixed partial differential equation, advection-diffusion term, or advection-diffusion equation. And the amplitude of the diffusion term depends on the time step you choose. And so, it's not your numerical solution will have differing amounts of diffusion depending on this kappa here. And that's why it works, because you've explicitly added diffusion to the solution. You're solving a different equation, a so-called modified equation. And you're getting a stable solution using finite differencing because you're solving a mixed differential equation with explicit diffusion. So that's why Lax-Friedrichs works. I would never recommend using Lax-Friedrichs today because this diffusion is enormous, relatively speaking. And so it completely swamps the solution in any useful astrophysical application. So we can do much, much better than this nowadays, but it's at least a stable method. A better way to go is to use so-called upwind methods, where now we choose the spatial derivative using one-sided differences. So going back to this picture on the board here, so I'm going to choose a difference molecule that couples the time derivative at point j, so un plus 1 and un at point j, and then I'm going to choose the spatial derivative either using these 2 points or these 2 points, depending on which way the flow is going. If the flow is going that way, then I would choose this these 2 points to calculate the spatial derivative. If the flow is going that way, I would use these 2 points. So I'm using the upwind points to calculate the spatial derivative. And it turns out that works remarkably well because, again, you can write the finite difference equation. Well, first of all, you can do the von Neumann stability analysis. You can work it all out and show that, once again, this is stable provided you satisfy the CFL condition. And moreover, you can rewrite the finite difference equation in the same form of this modified equation of a linear advection equation plus an explicit diffusion term. Once again, upwind methods are adding explicit diffusion, but now the diffusion coefficient is different. It's smaller. If you take the ratio of kappa, the diffusion coefficient for upwind methods, and you divide it by the kappa from Lax-Friedrichs, you get the CFL number. You get this quantity delta t over delta x over a. In some sense, it's the ratio of the time step you were using to the maximum time step you can use. And so if c is less than 1, this ratio is less than 1, and therefore the amount of diffusion you're adding with upwind methods is less than the amount of diffusion you add with Lax-Friedrichs. And it turns out, using so-called higher order methods, you can make this diffusion coefficient even smaller. So small, it makes these methods very, very useful, very, very powerful. So this is the fundamental differencing approach we use in finite volume methods, or these so-called upwind methods. And it's important to recognize this truncation error that we've been adding. We've been adding this diffusion error to the equations is strictly diffusive. So these equations, or this modified equation we're solving, is this mixed advection diffusion equation. And so Lax-Friedrichs and first order upwind are strictly diffusive. Not all methods add strictly diffusive error. Some methods solve a modified equation which, instead of depending on even powers of the derivative, depend on odd powers of the derivative. That is to say, the truncation error is associated with terms that depend on odd powers. And as you may know, those PDEs that contain odd powers have dispersive error, a dispersive nature. That is to say, the phase speed of modes of different k, different wave numbers, will propagate at different speeds. And so if I take a solution which is an admixture of many different wave numbers, they're all going to propagate apart at different speeds, and the solution gets lots of wiggles in it, it becomes dispersive. So when you solve advection problems using upwind or Lax-Friedrichs, then the initial analytic solution here just diffuses away into a blob. I mean, you'd like to make this better, but it's just diffusing away. Whereas if you use, for example, Lax-Wendroff or other high-order central schemes, if they are not carefully designed or they don't include so-called hyperviscosity to damp out the term with the odd powers of derivatives, then you can get these wiggles. So the solution doesn't just propagate, it propagates and introduces these wiggles. And this can be very, very bad in hydrodynamics and MHD because, for example, if this quantity is the density, and I'm advecting the density, and this is 0 here, then notice it's not 0 there, it's negative. The solution will introduce negative densities. Your code will crash because you'll be taking square roots of densities somewhere. So this dispersion error is extremely disruptive, if you like, to the method because it will inevitably make the method fail. Diffusion error is acceptable. Dispersion error needs to be avoided at all cost. Diffusion error can be controlled. Dispersion error is sort of fatal. It'll make your code have very bad properties and should be avoided. And so I'm only going to discuss methods which actually fundamentally only have diffusion error. Yes? Question?
So would you be able to stand out those higher frequencies in the Lax-Wendroff scheme, whereas in your first order advection scheme, you're diffusing even the features that you want? So is it really, so the Lax-Wendroff scheme really as bad as that, where you can't do anything about those dispersive areas, you can't damp those away?
Now there are fixes to Lax-Wendroff, and they typically involve adding filtering or diffusion for the highest wave numbers involved so that you damp them away. And that helps get rid of the dispersion error for the modes that are sort of most destructive. But then you're sort of losing some of the beauty of Lax-Wendroff because you're adding diffusion explicitly. And it becomes a game to decide how much you need to add to keep it stable versus how little can you add so that you keep it accurate. it's possible to do that, and you know, many methods are based on that. I just bring this up as a point of fact that if you're using Lax-Wendroff or other typical central schemes, then you need to be aware of this. And again, in modern numerical analysis, there's lots of ways to try to fix this, but you need to incorporate those fixes. You can't just use the raw method without those fixes. Okay, so it's all about keeping solutions so-called TVD, total variation diminishing, not allowing new extrema to appear in the solution. And keeping schemes TVD is a very, very important aspect of doing hyperbolic conservation laws. Okay, any other questions? Okay, so I've done with my basic introduction of the salient points of MHD relevant to numerical methods, and I've done with my most basic introduction with numerical analysis in 5 slides or less. And so let's talk about actual methods that we might use in astrophysics, finite volume methods. There's this, as I mentioned, all kinds of methods. Finite differencing with hyperviscosity to prevent dispersion error, because it's higher order finite differencing methods that needs hyperviscosity to prevent the kind of solutions I'm talking about. Operator split methods like Zeus, which avoid that dispersion error because they're actually based on upwind advection methods for the transport, but still need things like artificial viscosity to capture shocks. Central schemes, which are higher order versions of Lax-Wendroff today. Most people don't use Lax-Wendroff, but there's a whole zoo of methods. Tadmor-Kurtigan central methods. We know schemes can be thought of as central schemes. Various forms of finite volume schemes. I'm going to talk about Godunov methods. There are spectral methods that are useful for incompressible flows, but and can be used for weakly compressible, but you know, their weakness can be shock capturing in very compressible flows. I won't say much about lattice-Boltzmann, but they're another way. And again, I mentioned discontinuous Galerkin as they're definitely an emerging method that are used a lot in engineering and have a lot of attractive properties. We'll hear more about that in this school. But I'm going to focus again on these finite volume schemes. I can't cover them all. I'm going to just focus on one class of these methods. And even this one class, there's gazillions of codes. I mean, one way to know that these methods work is that so many people use them nowadays. So they've become, I would say, from looking at the literature, they're by far the most popular class of methods used in astrophysics for compressible MHD. And I just mentioned a few publicly available codes that you can download and use for this problem. And I'm sure I've forgotten some. Anybody's code I've forgotten that I should be mentioning here? Anybody want to speak up? You know, I only say publicly available, so it'd have to be a code that you'd be willing to give to somebody to use. So, I couldn't have got them. Yes? So yes and no. So all of these methods fundamentally adopt an upwind discretization which is stable. However, the exact implementation of the method in, say, curvilinear coordinates, or if there's extended physics, that may or may not be stable depending on the code developers and testing. And honestly, the parameter regime. I mean, codes are often work in some parameter regime, but not in others. No code does everything all the time. And so it is a little bit of buyer beware. You know, you can download these codes, and including Athena, which I've been working on. I'm not going to tell you Athena can do everything. It certainly can't. You can easily break Athena by using it in regimes where it was not meant to be used. And so you as a user have to be certain that your problem matches the strengths and weaknesses of these codes. And you should choose which code you want to use based on your problem and the learning curve and everything else. But there's no simple formula that I can give you that you can just check as to whether it works or doesn't work, I'm afraid. It's more complicated. Okay, well, maybe I didn't forget one, but I'm sure I have, and maybe if people later want to tell me more, I'm happy to put more on this list. But the point is there's a lot. I mean, there's a tremendous number of person years that have gone into writing these codes, that are making them available for people to use. So it's really a great aspect of astrophysics that people share their methods. And many, many years of work go into these methods, and they make them freely available for people to use. That not every community is like that. And astrophysics is quite unique in being able to share its methods. So I'm going to focus mostly on the methods that are contained in Athena. And that's very similar to methods in many of these codes. Pluto, Enzo, Flash, to some degree Harm, all contain methods. Ramses, for sure, all contain methods that are very, very similar to what I'll describe here. So with finite volume methods, okay, start at the beginning. How does this work? You solve the equations by, first of all, discretizing space into cells. So your continuous independent variable x turns into a set of discrete values, x of I, y of j, z of k. You have a 3D array of these discrete values at which you know the solution. You also discretize time into discrete levels. Time becomes a discrete set of n values, which are not necessarily equally spaced. The time step can vary as the evolution evolves, and so some time levels are more closely spaced than other time levels. So this is the picture in 1D. You discretize in space, you discretize in time. And then your continuous dependent variables like density, which analytically are functions of x and t, become discrete values stored on this ijk mesh at time level n, where it's very important to note that these are volume average values. They're the integral of the analytic solution over the volume of the cell and at the time level t divided by the volume of the cell. And so you throw away internal information about the solution to just store a volume average discrete value at the cell. These are not point-wise values. This is not the solution sampled at the point xi, yj, zk. It is the integral of the solution over the cell. That's a very important distinction. Finite differencing is a point-wise sampling. Finite volumes are the volume average, at least a very different set of discrete equations depending on whether you're doing finite differencing or finite volume. So we're doing finite volume, so this is Athena. So even with that, a code like Athena still uses a staggered mesh, and that only the density, total energy, momentum, or velocity are stored at cell centers in this volume averaged way. The magnetic field, in fact, is best to be represented on cell faces. And so the cell quantities are volume averaged, as I've just written, but actually, if you look at the induction equation, it's not a divergence of a flux, it's a curl of an electric field. It's not a divergence operator, it's a curl operator. And so you don't want to use Gauss's law, you don't want to integrate over a volume and compute a flux, you want to use Stokes' law. You want to integrate over an area and have a line integral around the edge. And that tells you, just from the mathematics of the equations alone, you know that magnetic fields should be area average quantities. They should be integrated over an area divided by the area, and then the time evolution of the magnetic field is just the integral electric field around that area, and the time evolution of the cell-centered quantities is the divergence of the fluxes through the faces. You can force the magnetic field into cell centers, and you can use volume, you can use divergence theorem and so on, but I just think that mathematically it's just sort of a lot cleaner to do it this way, for reasons we'll get to in a moment. So the discretization then is straightforward. So we have this hyperbolic conservation law in 3 dimensions. Time rate of change of this vector of conserved quantities used is a flux in the x, flux in the y, flux in the z directions. You integrate this over the volume of a grid cell and over a time step dt, apply the divergence theorem to this equation. You get that the time rate of change of the volume average quantity u at time level n plus 1 minus the time rate of change of that, the difference between these values, is just the difference between the integral of the fluxes on the faces of the cell. So I use this half index notation to represent the face which is halfway between I and I plus 1. And I minus a half is the flux that's halfway in between in the back. And I'll draw a picture in a minute so you can see this. And in the y direction, it's the j plus a half, j minus a half. In the z direction, k plus a half, k minus a half. And it's important to realize that this equation is exact. There is no approximation used in writing this equation. This equation is accurate to every order. It's just stating a conservation law. The approximation comes in when we write down the fluxes. We haven't done that yet. But if we had an infinitely accurate way of estimating the flux at the surface over the time step delta t, this would be the analytic solution. But at some level, we're going to have to approximate the fluxes, and that's where we make approximation. But this equation itself is exact. So where, just for completeness, this U is this average over the cell volume in each dimension of the actual analytic solution U. And these fluxes, here's the key, they're integrals not only over the areas of the face. So in the I direction, you know, you have a face in the I direction that has width in J and K, so there's an integral over Y and Z, but there's also an integral over time. This is the time average flux over the time step delta T. And figuring out what that time average flux is the whole name of the game here. How to get accurate representations of these time average fluxes, this F, G, and H here is the whole name of the game in doing numerics. Now, for the induction equation, we do not want to use this finite volume discretization. We want to use a finite area discretization. We want to integrate the magnetic field on an area, and then the time rate of change of the magnetic field located at the face. See, it's got labeled with I minus a half because it lives on the I minus a half x face. It's just the line integral of the electric field around the edges, the Y and Z edges of that face. And so it has these four terms, which are just each edge summed up. And this electric field is the integral over the line and in time. It's the time averaged line integral of the magnetic field at the cell edges. So you have one for the x component, one for the y component living in the y faces, and one for the z component on the z faces. And again, these are exact. There's no approximation here. The approximation comes into figuring out what these time and line averaged electric fields are. And again, you know, this B is just this area average of each component on the appropriate faces, and these electric fields are the appropriate time and line averaged. So just for completeness, I write it all out. I don't expect you to notice that, well, you know, typos. I don't expect you to comprehend all this. Late at night, you can look through your notes and see whether this all makes sense. So just to summarize in a picture, we have the volume average conserved variables located at cell center. They're integrals over the volume of the cell. We have the magnetic field components at cell faces in the X, Y, and Z faces labeled with this half integer notation to denote the edge of the cell in the I and J and K directions. And these quantities are updated using fluxes. So the cell center quantity U are updated using fluxes that are located at the cell faces. So F is at the cell face. It's the same location as BX. And H is the same location as BZ, and so on. And so the difference between the fluxes on each of the 6 faces of the cells gives you the time rate of change at the volume average quantity U. Whereas the electric fields here are located along the cell edges. So they have this half integer notation to note they're at the edge of the cell. And again, the time rate of change of the X magnetic field is just the line integral, the sum of these 4 electric fields around the edges. And the key here is how to compute these fluxes and electric fields in an accurate way. That's the whole game here. If we just knew those analytically, we'd be done. Okay, so how do we do that? So we use Godunov's method, a brilliant idea from the 50s from Godunov. So he realized that if I think about this problem in 1D, and let's forget about MHD, let's go back to hydrodynamics. So you can think of the solution for the volume average quantities in one dimension as being the sort of histogram. Each cell has a volume average value Q. So there's a value at Qi minus 1, Qi plus 1, and so on. So you can imagine your initial condition at any time step is just a bunch of piecewise constant values in every cell. So if I wanted to compute the evolution of this analytically, what would I do? Suppose I could just solve the so-called Riemann problem. The Riemann problem is how 2 discontinuous states evolve in time. If I could just compute how this change between Qi minus 1 and Qi evolves in time, I could then integrate the resulting solution over the cell and calculate the answer. So that's shown schematically here. Suppose this was pressure. This is a higher pressure here than here. That's going to launch a shock wave that way, a rarefaction that way. So at some later time, this interface will evolve into this shape here, shock wave moving that way, a rarefaction moving that way. And then it'll go the opposite way. The shock wave will go that way, and rarefaction, and so on and so forth. Every interface will evolve independently. And if I could just take the solution over the cell and integrate this curve, I would know what the new value is at the next time step. So, analytically, there's a clear way forward to how to compute the time evolution of these quantities. But what Godunov realized is that I don't need to compute this solution in detail. See, it's quite difficult to calculate the shape of this solution exactly and then integrate it in space to get exactly what the new value of the time average quantity Q should be. But the point is, you don't actually need to do that because we have these conservation laws. In fact, all I really need to know is the flux of the quantity through this interface here. And the time rate of change of the quantity here is just the difference of the fluxes here. All I really need to know is the flux through this face here. And the flux is just given by the solution to the so-called Riemann problem along this axis, x equals 0. If I just know the solution, not everywhere, if I just know the solution along this dotted line, that's all I need to know. So I can develop so-called approximate Riemann solvers that don't compute the solution everywhere, but they just compute the solution of the line x equals 0, and they compute that very accurately. So I get the accurate solution for the flux, and then I plug that flux into the difference equations, and then I can compute the time evolution of the solution. Then I just evolve this, once I know the flux along the line x, once I know the solution along the line x equals 0, I can compute a flux, I can put that in here, and I get the time rate of change of this conserved quantity. So the beauty here is I don't have to compute this complicated solutions using exact solvers. I can just compute the solution at discrete points at the interfaces, and that'll give me the flux, and that's exactly the same. It's just as accurate as getting at the full solution. So that's the beauty of this method. So that's how it works. So all we need to do is solve this so-called Riemann problem, calculate what that flux is. And so there's various ways to do that. And all the codes I mentioned, all these Godunov schemes fundamentally are based on Riemann solvers. And under the hood, there is some Riemann solver that they're using. And in pure hydrodynamics, there's many different choices. In fact, you can use exact solvers if you want, because they're not that expensive in hydrodynamics. But in MHD, and this gets back to the wave properties of MHD, there are 3 different wave families: fast modes, alphane modes, and slow modes. And there's a total of 7 characteristics, 7 different speeds at which wavefronts can propagate away from the initial interface. And in fact, some of those circumstances, these waves can be degenerate. As we saw from those Friedrichs diagrams, sometimes the alphane speed and the slow speed are the same, and sometimes the alphane speed and the fast speed are the same. And so when you solve the Riemann problem, you have to worry about all these different cases. And you got to figure out the solution along x equals 0 with all these different intermediate states, which sometimes that you're degenerate and sometimes that you're not. And so in fact, the fact that these eigenvalues are degenerate means that the equations of MHD are not strictly hyperbolic. Strictly hyperbolic systems of equations have unique eigenvalues. These MHD equations do not. Sometimes they're degenerate. That makes solving them that much more complicated. So in practice, people don't use exact solvers. It's just too expensive and complicated. And moreover, it's not really needed. We only need the solution along x equals 0. And so we adopt various methods. Rowe's method is a popular one. It's a linear decomposition of the equations, which keeps all the 7 characteristics, but treats them as discontinuities, simple waves. It doesn't allow for rarefactions. It introduces rarefaction shocks. That doesn't matter. They violate the physics, but it doesn't matter because it still gives you the solution on x equals 0 correctly. It gives you the right jumps. And it has various advantages and disadvantages. There are so-called HLL or HLLE methods. They keep only the largest and smallest characteristics. They make approximations. They throw away all the intermediate states and keep only one wave speed. There's even something simpler called local Lax-Friedrichs, which is actually quite popular. It keeps only one wave speed on both sides. It's only one fast wave, symmetric on both sides. They're very, very simple. They're guaranteed. They're very robust. But they can be very, very diffusive for the intermediate waves. And there's more extensions, HLC for hydrodynamics, HLD. And so part of your toolbox should be which Riemann solver you're using. And so again, this gets back to, will your code be stable or not? Well, it depends. Which Riemann solver is it using? And many codes offer many different Riemann solvers. Well, which one are you using for your problem? Rowe's solver sometimes breaks down because of the approximation inherent in it. So it'll work for some problems, but not for others. And so you have to know which Riemann solver you're using, I think, to really understand what's going on under the hood. So just as an example, so these various approximation for hydrodynamics can be pictorially represented as following. So here's these Riemann problems: position, time. Here's the exact solution. I have some state at time equals 0, which has a discontinuous jump between some, say large pressure and some small pressure here. And at time equals 0, in a self-similar fashion, this launches modes of the hydrodynamical waves. It launches a shock wave to the right, a contact to the right, and a rarefaction to the left. And so at any time, if I take a slice in X, I will get this rarefaction, contact, and then a shock wave. And what I want to know is the solution along that dotted line. That's what I need to know. I don't need to know what this rarefaction looks like. I just want to know what the solution is along this intermediate state to compute a flux. So here's Rho's approximation. It throws away the rarefaction, replaces it by discontinuity, a rarefaction shock. Sounds horrible. Doesn't matter because it gets the right jumps needed. In fact, along the dotted line, it gives you exactly the same solution as the exact. So the flux computed with Rho's approximation is exactly the same. For a single shock wave, Rho's approximation is exact. It gives you the exact same solution, and it's a lot cheaper and faster, so why wouldn't you use it in these cases? And then here's HLLE, which it throws away the contact, keeps only the rarefaction shock and the shock going to the right, and once again, it still gives you a good approximation to the solution along the dotted line. So which is best? Well, you got to explore the use of the solver in your application and decide which is best. And using these Riemann solvers is often viewed as a disadvantage of Godunov schemes because, gosh, they're slow and expensive. But in fact, it's why they're so good at shock capturing. You've built into the numerical method the analytic solution for the Rank-Huguenot jump conditions. You get shock waves exactly right. And so they have extremely good shock capturing properties that makes them very robust for shock physics, and that's why they're used they're so popular and so powerful in astrophysics. Now, what other ingredients are required? Well, we don't just use piecewise constant values to calculate the jump conditions at each interface. In fact, you can approximate the solution inside each cell using polynomials. If you just use a piecewise linear polynomial to fit the solution in every cell, then the left and right states that you choose to compute the Riemann problem would not be these two values here, which would be the Godunov's first order method, piecewise constant values. They're these two values here, which are much closer together. Therefore, the jumps are much smaller. Therefore, the dissipation introduced by the Riemann solver will be much less. So you get much less numerical dissipation when you're using higher order methods. Now, you don't have to use this piecewise linear. You can also fit it with piecewise polynomials. You could fit it with parabola, which would make this even smaller jumps and make it even more accurate and less numerical diffusion. You can go to fourth order methods, fifth order, eighth order. You can choose whatever high order fitting functions you like to construct these left and right states. And by doing that, you go to successively higher order spatial order in your truncation area. So the way you improve the accuracy of these methods is by introducing so-called reconstruction algorithms based on higher order polynomials, which also have a lot of pieces and bells and whistles. They need to be TVD, they need to be slope limiting, and I won't get into all of that. There's many papers you can refer to for the art of doing this reconstruction. So that's how you go to higher order in space. If you want to do multi-dimensions, the method I've described is strictly 1D. You're solving a 1D Riemann problem at every face to get the fluxes in 1D. Typically, what people have done is something called directional splitting. You solve the equations in the x direction using a one-dimensional approximation, and then you use that partially updated solution to solve it in the y direction, compute fluxes in y, and update everything in y, and then do the same thing again in z. And when you're all done, you've advanced the solution from time tn to tn plus 1 after one full cycle. You can also symmetrize the sweeps. You can do a half a delta t in x, delta t in y, delta t in z, half delta t in x, and so on and so forth. These are called Strang splitting to make it higher order in time. That can be used as well. But it turns out for MHD, this splitting doesn't work because it's impossible to keep div B 0 in these partial substeps. You can't update some of the components of B in an X sweep but not the others, and still keep div B 0. As soon as you update one component of B, you've broken div B equals 0. You have to update all three components of B at the same time. And so in MHD, you have to use directionally unsplit schemes using something, for example, called constrained transport. And to do that, there's so-called Runge-Kutta integrators, RK2, RK3. RK4 is kind of a sweet spot because going to RK5 is many, many more sub-steps to keep them TVD. So these RK Runge-Kutta TVD algorithms are quite popular. There's also something called Mussel-Hancock, which is very, very popular. And they're described in various papers in the applied mathematics and astrophysics literature. So the way you get to higher order in time is by doing multiple steps, multiple time steps as in a ODE integrator. You get higher order in space by higher order reconstruction, higher order in time using these TVD high order time integrators. And I won't walk through all the steps, but there they are. Some more practical matters of the implementation. You need to introduce boundary conditions for these PDEs. These are initial value problems, but they're also controlled by the solution at the boundaries. Well, how do you do that? Well, every code that I know treats boundaries using these so-called ghost or guard cells. So the actual solution is computed in this solid dark box. So the volume of the solution is bounded by this dark black line. But beyond the edges of the computational domain, you have extra cells where you store the solution. And you use those cells to compute gradients and fluxes. So you can compute the flux, say, at this interface here by using the solution not only on the active cells you're updating, but also the solution that's stored in these ghost cells. And by spatially interpreting the solution in the ghost cells, you get left and right states here that you need to compute the fluxes using a Riemann problem. And where do those ghost cell solutions come from? Well, they come from just applying some rule, some boundary condition. It could be periodic, in which case they're just mapped. These two values get mapped to there for a periodic boundary condition. They could be reflecting, in which case you just reflect the solution from these cells to these cells. So you load the ghost cells using special rules. You don't solve the PDEs in those cells. You just load the cells using whatever boundary condition rules you want, and then you use them to compute the fluxes where you need them. But some care is required to make sure you get everything in the corners and you have enough ghost cells. And most bugs in code seem to be related to not filling the ghost cells properly everywhere all the time. That can be problematic. How do we keep div B 0? There are a variety of ways implemented in different codes. One way is to do nothing. This was popular 10 years ago, not so much now. Just assume everything's okay. But you and I know what happens when you assume. That doesn't work very well. So another popular way 10 years ago was using vector potential. Sometimes it's still used today even. But it fell out of favor because computing the Lorentz force, curl of B, required taking a second derivative of A. And if you have discontinuities, taking numerical second derivatives across discontinuities can introduce ringing and can lower the order of the method in some circumstances. And so this fell out of favor because you don't need to use the vector potential. You can use the magnetic field directly. There's also something called flux cleaning, which still today is very popular. The early version just solved an elliptic equation every time. But nowadays, there's something called hyperbolic or Dedener cleaning, where the evolution equation for the divergence part of the field satisfies a hyperbolic equation, so the air is transported away at some wave speed. But it requires a tuning of parameters to damp the air and propagate it away correctly. And if you're doing relativistic flows, well, I mean, you can't propagate things faster than the speed of light, and you are solving things at the speed of light. And so whether or not the air gets away or not is an issue. There's something called Powell's 8-wave solver, but there's an influential paper by Toff which showed that this method doesn't actually work for some test problems. It gives the wrong jump conditions because it has a finite impulse due to the div B error at discontinuities. So finally, the method that we use, and I think is I think is a great way, is just solving the integral form deduction equation using a staggered grid for B. The method I described to you. You see the beauty of keeping the magnetic field in cell faces, and then using electric fields at cell edges, and then updating them according to Stokes' law, is that when you update Bx on this back wall and By, they share the same electric field Ez. And so every face of every face where it stores a magnetic field shares an edge with another face. And so when you calculate div B at the advanced time, it involves the electric fields that you use to advance the solution in terms that cancel each other. And so if div B was 0 initially, these electric fields will cancel away, and div B will guaranteed to be 0 at the advanced time to machine precision. In other words, it works exactly the same way that you conserve mass, momentum, and energy. By sharing fluxes at faces, you conserve the volume average quantities. Well, by sharing cell edges, you conserve area average quantities like magnetic flux. And so CT, you don't do anything special. It just automatically keeps div b equals 0. And so I find it a very attractive MAE. The problem with CT is that it introduces a staggered magnetic field. And you're solving a Riemann problem to compute the fluxes. That means the fluxes that you get are at cell faces, but you need them at cell corners because that's where you're going to evolve the magnetic field. And so somehow you have to turn the electric fields that come out of the Riemann solver at cell faces to corners. And how you do that matters. So in a 2D problem, for example, here's an example where we solved Riemann problems between these 4 cells. We've computed the fluxes of all the conserved quantities at these 4 faces, and that includes the electric fields we need to evolve the magnetic field. But the magnetic fields in 2D are stored at these faces, just like the electric fields. And so the real electric field we need is at corners. So how do we get these 4 electric fields to the corner? You can't just do arithmetic averaging. That destroys the upwindedness of the solution. You have to preserve the upwindedness. You have to choose which of these electric fields are the upwind electric field of this interface. And that's very important. And if you do that properly, it makes the method work well. I won't show this test in the interest of time. So another ingredient to the overall code is time step control. And we go back to the CFL condition. That's the fundamental limit for evolving the equations. Delta t has to be less than what amounts to the wave propagation time across the cell. In other words, in the frame of the fluid moving at velocity v, the fastest wave in the flow cannot move a distance more than delta x in the time step delta t. That's the physical interpretation of the CFL condition. And so the mathematical form of it is that delta t has to be less than the distance a wave can move in delta t. You got to take the minimum over every cell because in every cell you have a different v over and different c, and you have to use the fastest wave speed here, summed in the direction of the flow. You can use this sort of as a practical matter, but you can also derive it rigorously, as we did before, from a von Neumann stability analysis. In multi-dimensions, these RK integrators are limited by 1 over the number of dimensions. So in 1D, the stability limit is CFL number of 1. In 2D, TVD-RK methods are limited by CFL number of a half. In 3D, TVD-RK methods are limited by a third. That can be a little painful. I mean, your time step is 3 times smaller than it is in 1D, and that makes 3D simulations that much more expensive. But there it is. If you violate this condition, we don't have sympathy for you, basically. You know your solution is going to be unstable to some degree if you violate this. It's the law. You have to follow the law for this. So let me say a few things about how you know it works. And the test problems I think that make sense are those that are based, again, on the basic properties of solutions to hyperbolic equations, like linear wave convergence. Can you show that your method actually captures linear waves correctly and that it converges with the truncation or converges with resolution? Can you do shock tubes? Can you do nonlinear problems where there are known analytic solutions for the evolution of the shock? Can you reproduce those? Can you follow the nonlinear evolution of MHD instabilities, Kelvin-Helmholtz, Rayleigh-Taylor, MRI, etc.? In MHD, it's very important to use multidimensional tests because in 1D, the div B condition is trivial. It doesn't exist, basically. In 1D, the MHD equations look like hydrodynamics just with an extra pressure. And so if you're not doing multi-dimensions, you're not really testing whether or not your code is keeping div B 0, which is the most important aspect of MHD. Now, there's a web page with lots of different test problems associated with Athena code that we've used. That's a good starting point. And there's many other tests in the literature that you might use. And here's some examples. Linear wave convergence, you put an eigenmode of each wave family as the initial condition. You propagate it across the mesh using periodic boundary conditions, say for 5 wave periods. You then take the numerical solution and compare it to the analytic solution and compute the L1 error, the difference between numerical and analytic solution, and you plot that versus numerical resolution, number of grid points per wavelength, and it better be decreasing as you increase the resolution. This is done for fast modes, Alfvén modes, slow modes, and entropy modes. That's the contact discontinuity. And what's shown here is different time integrators. So you can see that the different ways of integrating the equations in time can give you different amounts of error. Even for the same reconstruction, same Riemann solver, you use different time integration algorithms, you can get different amounts of numerical truncation error. While they all converge at second order, the amplitude of the error at every resolution is a little bit different. And so you can figure out which is the best method, most cost-effective method by using these kind of tests. This is also a very powerful way to find bugs because you're measuring things down to errors of 10 to the minus 9. And if somewhere in your code there's a bug, this will just stop converging. The error won't get any smaller because you're doing something incorrectly somewhere, which is introducing a fixed amount of error which is not converging. So these convergence tests really are very powerful ways to find bugs. For example, one way we found useful is you run the wave to the left, and then you run it to the right, and it better be exactly the same to every digit of precision. And if it's not, there's something funny going on somewhere in your code. That proved to be very useful for finding bugs. Then there's shock 2 problems, which in MHD, they have to be in multi-dimensions, and so you have to have a multi-dimensional interface which should be inclined. You can't just do it parallel to the grid because then it's a bunch of 1D problems stacked on top of each other. So you have a left state and a right state, which is along some diagonal of the mesh, and then you have appropriate periodic boundary conditions on the sides. This evolves the shock wave or rarefactions, and then at later times you can plot profiles. This is from a 3D calculation. You can plot the profiles of the solution, compare them to the analytic solution. You can try different Riemann solvers to see how they behave. And then finally, KH instability is another very, very good test. A recent paper by Lecoine et al. Has been very useful because it provides a resolved reference solution computed with explicit dissipation using a spectral method. So it's sort of the absolute right answer. There's no debate about what the nonlinear evolution of the KH instability will be for those parameter values. And then you can test against that reference solution. You can try running a different code. Here's Athena running against Daedalus. A is Athena, D is Daedalus at different resolutions, and you can see whether or not Athena and Daedalus agree. And remarkably, they agree almost exactly between, Athena needs much higher resolution than Daedalus. Daedalus being a spectral method, it converges exponentially. Athena is only a second order Godunov scheme. But the point is, you can validate the method. Athena gets the right answer for this problem exactly. And this is another important soapbox rant here, is that test problems have to be known solutions, or they're not tests. You can't just run a problem for which you don't know the solution and say, oh, that looks great, and then run a different code, oh, that doesn't look as good. Because you don't know which one's right. I mean, maybe the one that doesn't look so good isn't right, is right, and the other one's wrong. I mean, you have to actually have a solution. And this is a good test because it turns out, there's much less structure in here than some other codes get. And that's right, that extra structure is actually wrong. And so it's not because these codes are diffusive and they're not getting extra structure. It's because that's the right answer to this problem, and that all that extra structure is coming from grid noise and is not the right answer to the problem. And so extra small-scale details doesn't make the code better if you don't know for sure that that stuff's supposed to be there. So you have to have known solutions. This is a really great one because it's one of the first known solutions for the Kelvin-Helmholtz instability that I'm aware of for resolved parameter values. And let's see. Okay, I'm not going to cover all of that. I'm almost out of time. I'm basically out of time. But let me cover this one last slide. Since I'm on my soapbox already, I'll just continue with some salient points about programming these methods. And these are maybe points of discussion later, actually, or one of the evening sessions. Here's my rants. Write modular code, makes it easy to understand, easy to extend. Most importantly, keep it simple. The problem with advanced languages like C++ is it's really easy to make extremely complicated code that's almost impossible to understand, and more importantly, it makes it impossible for the compiler to understand, and therefore the compiler reverts to the simplest, safest execution model, and it really hurts performance. So you really want to write simple, easily understandable modular code. Don't be too smart and try to abstract away everything into objects, because that just hurts everything. Make it easy to use, rely on standards, flexible output files, Make sure the code is portable. Adhere to ANSI standards. Don't use language extensions. That'll inevitably hurt you in the future when you try to run on some machine that doesn't have those extensions. Try not to use external libraries. It's some level impossible. You need at least the MPI library. But after that, try to avoid using libraries unless you really have to. Again, it's just going to hurt you in the long run when you try to run on some supercomputer somewhere that doesn't have that library installed, and therefore you can't do anything on that. Or you try to get them to install it, and it's just a nightmare. Performance is important. So figure out whether or not it's the memory or the floating point operations. Is it vectorization that's limiting it? You've got to profile your code. You've got to not just guess its performance, profile it. And unit testing, regression testing, absolute must nowadays. Tests must be known solutions. You have to be using SVN or Git if you're going to be writing a big code. It's absolutely essential for finding bugs, tracking changes, allowing multiple developers. There is a learning curve to this. I mean, people don't want to learn new things because it takes time. But trust me, the amount of time you will save by finding bugs in the long run is much, much greater than the amount of time it takes to learn these tools. So you really have to adopt the tools, bite the bullet, learn how to use them. They'll save you an infinite amount of time over the long run. And then finally, you need documentation because everyone thinks they're the only one writing the code and they know how to use it. That's never true. You always give the code to somebody else. And you'll spend more time explaining to them how to use it than you will writing documentation if you just write the documentation. So while you're writing the code, write the documentation. So these are all points I think that might be worth talking elsewhere. I think I should quit here. Time is up, right?